In this video, we will implement Python code to apply green eye or eye lens color, primarily using Dlib for face recognition and OpenCV's half-circle transform to detect the region of an image that depicts eyeballs. We will be using an image of a human face for testing our implementation. Dlib get_frontal_face_detector is used to return Dlib's face detector, and Dlib shape predictor object is used to output a set of point locations that define the pose of the face image. I've used the shape predictor _68_face_landmarks.dat face prediction model to create the predictor object. This part of the code is already implemented in the notebook, and I won't explain it further in this video. Let's dive straight into the implementation for applying green eye lens color to an image. We use the previously instantiated face detector object to obtain Dlib's face detection. We use the Dlib landmark detector object to predict the shape of a human face, that is, obtain a set of 68 point landmark locations which defines the pose of the supplied image. The image file is showing on your screen. The parts method of landmark detector provides the Cartesian coordinate location of all the 68 landmarks. My particular interest is in the landmark numbers 37, 38, 40, 41, which are for the left eye when viewing the image, and landmark numbers 43, 44, 46, 47, which correspond to the right eye when viewing the image. To apply green color, since the eyeballs are nearly spherical, we have used OpenCV's half-circle transform to detect the eyeballs. Our implementation uses the eyeball circles detected by half transform to identify the pixels in the region of the eyeballs. Using the HSV, that is hue, saturation, and value color model, the hue component of these pixels is shifted more towards green color. The saturation and value components are adjusted as needed to provide a more realistic appearance to the eyes. In other words, we move the color of the eyeballs towards green and alter the brightness or intensity of the portion of the image that represents the eyeballs. We need to supply the radius of the circle that half-circle transform is to detect for the eyeballs. We calculate the eyeball radius as approximately 1/2 of the distance between the landmark points 38 and 37 along the x-coordinate. We also calculate the distance between the two eyeballs as approximately 1/2 of the distance between the landmark points 45 and 38 along the x-coordinate. The distance between eyeballs will be used in half-circle transform, as we will see next. We proceed to call CV2 half-circles within our wrapper function call half-circles. The parameter dp of half-circles is the inverse ratio of the accumulator resolution to the image resolution according to CV documentation. We are setting dp is equal to 1, which means the accumulator has the same resolution, that is, same width and height as that of the input image. We have experimented with setting dp is equal to 2, which means the accumulator has half as big width and height, but we finally selected dp is equal to 1 for this implementation. We're setting min_dist, the minimum distance between the centers of the detected circles, as 1/2 the distance between the eyeballs that we calculated before. If the min_dist parameter is too small, we may falsely detect multiple neighbor circles in addition to a true one. If it's too large, some circles may be missed. So we may have to experiment with the value by which we want to divide this parameter. We're setting the detection method as half_gradient, which, as far as I know, is the only implemented method. We are setting the first method specific parameter, param1, to our edge_sensitivity_threshold, which has a value of 450. This is used as a sensitivity threshold in edge detection when using the half_gradient method. We are setting a value of 10 to our edge_accum_threshold, which is parameter 2. In case of half_gradient, the documentation states that it is the accumulator threshold for the circle centers at the detection stage. The smaller it is, the more false circles may be detected. So we may have to experiment with the value we set here. The parameter min radius, that is minimum circle radius, is set to the value of the approximate distance between the two eyeballs that we calculated before, trimmed further by subtracting from it a quarter of its own value. Similarly, the parameter max radius or maximum circle radius is adjusted by adding to it 1/2 of its own value. It is best to convert the image to grayscale before inputting the image array to half circles. We believe this helps reduce any noise from color, thus improving circle detection. We return the output vector of circles found by half circles. Next, we need to deselect all detected circles except the ones corresponding to the eyeballs in our image. According to the documentation, each vector in the output vector of circles returned by half circles is encoded as a 3-element floating point vector, that is xy coordinate of the center of the circle and the radius. Before further processing, we use numpy around to evenly round the floating point values. Then we call the function select eye circles, in which we have implemented the mean square distance method to select the two circles whose centers lie at the shortest distance from our left and right eye landmark points, respectively. First, we declare two distance vectors, left underscore distances and right underscore distances. Then we loop through each circle in the half circles vector. We calculate the root mean square distance of the center of the circle from each eye. In calculating the root mean square, we divide the sum of square differences in distance with the value of 8. Remember, we considered 4 distance points for an eye, and since each point has xy coordinates, we multiply the 4 by 2 to get to a value of 8. The root mean square distances are stored in variables rmsd underscore left underscore eye for the left eye and rmsd underscore right underscore eye for the right eye. We append the calculated root mean square distances of each circle from the left and right eyes in our vectors left underscore distances and right underscore distances respectively. Next, we select the circle closest to the left eye by finding the index of the minimum value in the left distance vector and retrieving the circle at the same index of the half circles vector. Likewise, we select the circle closest to the right eye. Finally, we return the selected left and right half circles as a 2x3 matrix in which the rows are represented by the two circles. Next, we need to identify the pixels in the eyeball region. These pixels are in the region identified by the two half circles we selected. We call the function create histogram of HSV in eye region and pass the two half circles to it. We draw the two circles on a grayscale version of the image and apply RGB values 255, 255, 255 to them to color them pure white. Then we divide the entire gray image array by 255. This sets the pixel RGB values for the two half circles to 1. We can then use this as a mask to filter out the pixel indexes in the image array corresponding to the eyeball region and store the indexes in eye underscore pixel underscore index. Next, we convert the image array to HSV model and split it into individual hue, saturation, and intensity or value channels. We extract a vector of pixel hue values from the H channel indexed by values in eye underscore pixel underscore index. Likewise, we extract vectors of pixel saturation and intensity values from the S and V channels respectively. Then we construct numpy histograms for each of these three vectors. The bin values I set for hue, saturation, and intensity or value were after some experimentation with the original image array. We return the three histograms and the eye pixel vectors and indices from this function. Next, we call the function change HSV of histogram and pass our 3H, S, and V histograms, the eye pixel vectors, and pixel indices to the function. In order to change the eye pixel color to green in this function, we create three numpy arrays with hue, saturation, and intensity values, respectively, that we want to replace the original pixel values with. The numpy arange function returns a numpy array with evenly spaced values within supplied intervals for the color green. I've set specific interval values for hue, saturation, and intensity, which I determined after some experimentation. The main hue, saturation, and intensity pixel values of the eyeball region of the original image have the highest frequencies in the HSV histograms. We try to pick up to 40 consecutive highest frequencies of the original HSV values in the function get largest adjacent frequencies. Numbins is the parameter to set how many consecutive highest frequencies we want. The function basically sorts the histogram in descending order to capture the indexes of the highest 40 frequencies. These indexes are nothing but actual pixel values in the HSV vectors. Using these values, we do a reverse lookup to find corresponding indices in the HSV vectors. We then replace the HSV pixel value at those indices with desired values for green color and propagate the changes to the HSV image arrays. This has the effect of replacing the eye or lens color with green. Finally, we display the new image array after merging the replaced HSV channels that contain the replaced pixel values for the eyes. This completes the implementation. We hope you like this video.